Hi everyone, I am Madam Rosmaya. In this video, we are going to discuss on topic wave particle duality. The topic, most of the question is about the Broglie wavelength. And before you watch this video, make sure you have uh, done the question given in the link to the PDF question given in the description below the video. Okay, so we go to the first question. Calculate the wavelength of a 0.15 kilogram ball traveling at 0.12 meter per second. Then a neutron of mass 1.67 times 10 to the power of negative 27 kilogram traveling at 6.2 times 10 to the power of 4 meter per second. Okay, for first question, you are given mass of the ball and velocity of the ball. So the formula we are going to use is the formula de Broglie wavelength, which is lambda equals to h over h is a Planck constant over p is a momentum. Okay, momentum is mass times velocity. So we substitute Planck constant 6.63 times 10 to the power of negative 34 and divided by the mass given 0.15 kg and the speed 0.12 meter per second. So we get the wavelength is 3.68 times 10 to the power of negative 32 meter. So it's a very small wavelength. Okay, for a neutron, we use the same formula and we substitute the mass and the Planck constant and the speed. Given 1.67 times 10 to the power of negative 27 kilograms. So that's the mass of neutron. Speed 6.2 times 10 to the power of 4. So we get the wavelength 6.40 times 10 to the power of negative 12 meter. So when now compare these two value, we find that the wavelength of the ball, okay, traveling at this speed is much smaller compared to the neutron, which traveling at larger speed. But the mass is very small. Okay, so we go to the question 2. Question 2. Okay, calculate the wavelength of an electron with a kinetic energy of 15 electron volt. So given that the mass of electron is 9.11 times 10 to the power of negative 31 kilogram. Okay, this time the question gives kinetic energy. Okay, so how we are going to relate with the wavelength using the de Broglie wavelength. So de Broglie wavelength is equals to the Planck constant over momentum. Okay, so because kinetic energy is given, so we combine with the P to get a new equation. Okay, combine these two. So for kinetic energy, half mv squared. So we multiply by m and also divide by m. So we don't change the equation actually. So why? Because we are going to relate with P. So m times m here. This is m squared and v squared. We get m squared v squared. So we can substitute momentum here. So we get half p squared over m. Okay, so we cross multiply, we get P equals to square root of 2mk. So now we combine with the de Broglie wavelength and we get new equation. Wavelength equals to Planck constant divided by square root of 2mk. M is a mass and k is a kinetic energy. Okay, now we substitute all the values given here. Kinetic energy 15 electron volt. So this 15 electron volt we need to convert to SI unit, joule. So we multiply by 1.6 times 10 to the power of negative 19. So we get the electron volt unit here to joule unit. The rest all is in the SI unit, Planck constant and the mass of the electron. And we get the answer, the wavelength is 3.17 times 10 to the power of negative 10 meter. So that's the answer. Now we go to question 3. Okay, find the kinetic energy of a proton with a wavelength of 0.20 meter. Mass of proton given as 1.67 times 10 to the power of negative 27 kilogram. Okay, so the question is one kinetic energy. Wavelength is given and mass of proton is given. So we use the Broglie wavelength formula. So we have derived the new equation for the wavelength using the combination of momentum and the kinetic energy, and we substitute into the de Broglie wavelength. So we get this equation. So I no need for us to repeat how we get the equation. Okay, we substitute all the values given, and the answer is already in joule, right? Not in electron volt. So if the question asks to convert to electron volt, you can divide by 1.6 times 10 to the power of negative 19. You get in electron volt. Okay, now question 4. A moving proton and a moving electron have equal wavelengths. Determine the ratio of the kinetic energy of the electron to that of a proton. So mass of electron given and mass of proton also given. Okay, so we use the Broglie wavelength. Okay, and combine the momentum and the kinetic energy. So from this equation, we divide. There are two situations given here: proton and electron. So for the electron, the equation is H over square root of 2 times mass of the electron times the kinetic energy of electron. And for proton, wavelength of proton equals to H over 2 times mass of proton times kinetic energy of the proton. Okay, to get the ratio, equation 2 divided by equation 1. Because the questions 1, kinetic ratio of kinetic energy of the electron to that of a proton. So 2 divided by 1. Okay, lambda E over lambda P. Okay, wavelength of electron over wavelength of proton. Okay, so now we cross multiply here to get kinetic energy of electron to the proton. Okay, the wavelength can be cancelled out because mentioned in the question they are equal. Okay, Planck constant also can be cancelled out. So we get kinetic energy of the electron to the proton equals to, and we square root both sides. Okay, because here we have square root. So squaring both sides, we get the answer 1833, and the ratio kinetic energy electron to proton is 1833. Okay, now we go to question 5. What is the wavelength associated with electrons that have been accelerated through a potential difference of 28 kilovolt in a vacuum? Charge of electron given and mass of electron given. Okay, so the voltage is given, or potential difference, in kilovolt, charge of electron and the mass of electron. So how to relate this with the Broglie wavelength? So we use H over square root of 2 mk, and the and k is eV in electron volt. So the kinetic energy in joule we convert to electron volt. Okay, because from the principle of conservation of energy, actually, from the principle of conservation of energy, so the kinetic energy half mv squared, change in kinetic energy half mv squared equals to the ev. Okay, so now we substitute everything into the equation, and we get, okay, everything is in SI unit already, because coulomb. Okay, coulomb is in SI unit. Okay, now another one, 28 kilovolt. Okay, we need to convert to volt. Okay, all is in SI unit already. So the answer is 7.34 times 10 to the power of negative 12 meter. So that's the answer for question 5. Okay, now we go to question 6. How many volts of potential difference is needed to accelerate an electron in order to obtain a wavelength of 0.12 nanometer? So mass of electron is given. Okay, we are going to find potential difference. Okay, now we use the Broglie wavelength. Lambda equals to h over p, and and it's also equals to h over square root of 2mk. And from the principle of conservation of energy, so kinetic energy is equals to the EV. Okay, so now we substitute, we are going to find a potential difference. So we arrange the equation so that we get V. So squaring both sides, we get lambda squared equals to h squared over 2 MEV, and V equals to h squared over 2 ME lambda squared. So now we can substitute everything. Okay, make sure all is in SI unit. Okay, check. Nanometer. So here 0.12 nanometer convert to meter. Okay, now the answer is 105 volt. So that's the answer for question 6. Okay, now we go to question 7. In the Davison-Germer experiment, the electrons are accelerated from rest through a potential difference of 2500 kilovolt in a vacuum. Determine the de Broglie wavelength, the momentum, and the kinetic energy of the electron. So given mass of the electron and charge of the electron, and also the Planck constant. Okay, so for question A, the de Broglie wavelength. Okay, we use the de Broglie wavelength equation, Planck constant over momentum, and and another equation is h over square root of 2mk, because here given okay, given potential difference, so we use another one, k equals to ev, from the principle of conservation of energy. So we use h over square root of 2 MeV. Okay, so now we substitute everything given here. Planck constant, 2 mass of the electron, and electron charge 1.6 times 10 to the power of negative 19. Okay, there is a mistake there, typing error, negative 19, and the voltage is in kilovolt, so convert to volt. So the answer is 7.77 times 10 to the power of negative 13 meter. Okay, so now next is the momentum. Okay, to find the momentum, we use the above equation, lambda equals to h over p. So lambda wavelength calculated already, so we substitute into the equation. So cross multiply to get p, and we get the answer 8.53 times 10 to the power of negative 22 kilogram meter per second. Okay, and lastly is kinetic energy. So kinetic energy of the electron, we can use the relationship between momentum and the kinetic energy here. So I repeat what we do just now, the previous question. So the kinetic energy half mv squared, so multiplied by m and divided by m. So we don't change the equation, but we can relate it with p. So the top, here we get half m squared v squared over m. So mv is the momentum, so half p squared over m. And the momentum from the equation B, from the answer B, from question B, we can substitute into the equation. Okay, this one, 8.53 times 10 to the power of negative 22. Okay, don't forget squared, divided by mass of the electron, and we get kinetic energy 3.99 times 10 to the power of negative 13 joule. Okay, that's the answer for 7C. And the last question, question 8. A microscopic object is observed using an optical microscope. The optical microscope uses visible light of wavelength 6 times 10 to the power of negative 7 meter. An electron microscope using electrons which have been accelerated through a potential difference of 4,800 volt is used to observe the same object. So compare the resolving power. Okay, so we have light microscope and electron microscope. So the light microscope use principle of light, and the electron microscope use the principle of electron. Okay, so now wavelength given electron, we know that the charge of electron 1.6 times 10 to the power negative 19, and the voltage used in the electron microscope is given to accelerate the electron. Okay, so it's 4,800 volt. Okay, from the de Broglie wavelength, and h over square root of 2 mk, and then k equals to ev. Okay, so we get substitute the all the values, mass of the electron charge, and the potential difference already in volts. So we get the wavelength 1.77 times 10 to the power of negative 11 meter. Okay, so we see here, since the wavelength of the electron microscope is 1.77 times 10 to the power of negative 11, so we divide by the visible light wavelength. So we get 1 over 34,000 times. So this one is the wavelength of the electron microscope. It's a 1 over 34,000 times that of visible light. So the resolving power of the electron microscope is approximately 34,000 times of that of an optical microscope. Okay, so that's all for tutorial 18, and see you in the next tutorial.